Thank you. So thank you for, I'd like first to thank the organizers for hosting this conference and for allowing me to share my work. Before starting up, I want to point out that this is a joint work with Vincent Pilot, everything I'm going to talk about. As a brief outline, the first thing I'm going to talk about are basic recollection on lattices and canonical joint representations. Afterwards, I'll be able to introduce the weak order and permutations that has been introduced in the previous talk, but I want to have a very specific point of view for the type A Coxeter groups. And finally, I'll be able to introduce what we've been working on with Vincent. Okay, so let's start easy. Everything I'm going to work with is going to be finite, and I'm going to be working with lattices that are finite posets, where every family of elements admits a join element that we denote like this, the smallest upper bound, and as well a meet element that we denote like this, that's going to be a greatest lower bound. Now, what I'm going to be interested in are canonical join representations in the lattice. So there are a way, given an element of the lattice, to see it as a join of a family of elements. And I want this family to be both inclusion minimal. That means if I get something smaller, I want the join of the smaller family to be another element, something lower in the poset. And I want this family to be as well minimal in the poset, as low as possible. So these do not always exist, but when they do exist, we call the lattice join-semidistributive, and these are the lattices I'm going to be working with. Now, on an example. So this poset is a lattice, trust me, and it is join-semidistributive, trust me. And we're going to see how we can label its vertices with canonical join representations. So the first one is the bottom one, is quite obvious. It's just join of nothing. Join of nothing is the bottom element. Trust me. Then this one over there, we can't really label him as a join of something else than himself. Maybe you can see it because it only covers one element, so you can't really write him as a join of two elements. So we just give him a name, call him A. The second one behaves just the same way, and the third one as well. So we just call them B and C, and then it started getting interesting, as this one we can see as the join of everyone below, but that's not minimals, in inclusion minimal. So we're just going to label him A join B, and the three other ones here behaves just in the same way. So A join C and B join C. This one here, maybe you can see, is the join of A, B, and C. The two above here behave just as those three. So D and we just give them new names. And finally, this one, well, we can write as the join of D and E, but A and E is also a valid candidate and is lower in the poset. So that's how we're going to label it. Okay, so that's a long example. We're going to follow him throughout the whole talk. And what can we see on this? What can we observe on this first run of our example? So we have these elements, A, B, C, D, E, that play a very special role. So we call that they are their own canonical join representations. And since we're in a finite lattice, it means that they cover only one element. And in this sense, we're going to call them join irreducible elements. The other observation we can make is that the canonical join representations are made of join irreducible elements. And a nice way to encode this, a very natural way to encode this, is through a simplicial complex structure. We call it the canonical join complex. It's been introduced by Nathan Reading in 2015. And so it just is a simplicial complex whose vertices are the join irreducible elements, and the faces corresponds to the canonical join representations. So one thing that was proved about this canonical join complex is that it is a flag simplicial complex, and I'm going to explain what it is on our example again. So this is our example, still labeled with canonical join representations, and this is the corresponding canonical join complex. So the definition says that since I have, for example, an A join B here, it means that in my complex, I should have an edge between A and B. The vertices are the A, B, C, D, and E joint irreducible elements, and I just labeled them with a little join symbol to avoid confusion later. So in the same way, we have ABC, that is a canonical joint representation. So that means we have this whole triangle. Now I said that this is always flag. And well, there are nice way to say this, but the way I want to think about this is that whenever I got the 3 edges of a triangle, I must have the whole triangle as well. And similarly for higher dimensional simplices. So whenever I want to give you a canonical joint complex, I'm just going to draw edges. It's going to be enough to recover the whole structure. Now, another thing I'm going to be working with lattices is congruences. So lattice congruences are equivalence relation that behaves well with join and meet operations. These are more formal statement, but really think of them as the natural way to build an equivalence relation when you have a join and meet operations. So this has been widely studied. We can show that their classes are always intervals. That will be useful later. And they allow to think about the quotient lattice that is just going to be a lattice structure on the classes of the relation. Now, a couple properties of these congruences. They are completely characterized by the sets of joint irreducible elements contracted in the congruence, that is, that are merged with the one that they cover. We're going to see that on the example right afterwards. And we can make the statement even more precise by defining a poset structure on the joint irreducibles. That's called the forcing order. And the joint irreducible that can be contracted by congruence are going to be upper ideal of this congruence. So again, okay, before I have to say that this these lattice congruences and the canonical joint complex really like each other. They behave really well together. And I'm going to make this more precise on the example again. So here's our lattice again. And below is our canonical joint complex again. And I'm not going to tell you how I did that, but here's the forcing order of this lattice. I'm not going to say how I computed it, just trust me. And so we have to pick an upper ideal of this forcing order. So what I'm going to do is just draw a line and pick everything that's above. So I'm going to contract the joint irreducible elements A and D. So how do we build our congruence? So first we take a copy of our lattice, and then we want to contract A and D. So we got to merge A with the bottom element and D with this A join B join C. So these edges will be contracted. Now, this will enforce some other contractions in the lattice. Again, I will spare you the details. These are all the edges that are going to be contracted in the quotient. What I mean is that this here is a class of my congruence. This is a class of my congruence. I have 5 classes in total. Now, one neat way to see the quotient lattice with this drawing is just to look at the induced poset by the poset induced by the bottom elements of all of my classes. And so this is the quotient lattice associated to this ideal of the forcing order. So now I think this is clear. I just need to make precise the statement about the relation between canonical joint complexes and lattice congruences. So again, we take a copy of our canonical joint complex, and maybe you can see it here. The elements that are in gray that I hope you can see are all those that have either an A or a B or both. So the statement is that the canonical joint complex of the quotient is going to be generated by these black elements here, the ones that are not contracted. So you just remove A, remove D, keep everything else. And this is the canonical joint complex of the quotient. All right. With this out of the way, I'm going to be able to talk about the weak order. So very briefly, the weak order, I'm going to be talking about the right weak order, is a semidistributive lattice on permutations. They are ordered by containment of inversion sets. We've seen this half an hour earlier. Very briefly, in the case of permutations, the inversion set of A permutation is just the set of pairs of elements that are sorted in decreasing order in the permutation. So here's 1, 3, 2. The only pair of integers that are ordered in decreasing order is the pair 2, 3. So this is its inversion sets. It is a subset of this one, which is the inversion set of that permutation, which means that in the right weak order, the permutation 1, 3, 2 is smaller than 3, 1, 2. These are the weak order of size 2 to 4, and indeed you can check here that 1, 3, 2 is indeed lower than 3, 1, 2. Okay, I'm not going to care about this at all, in fact, because what I'm going to be working with is another way to see permutations that will make the work way easier. It's a very nice bijection from a paper of Nathan Reading in 2015 that I'm going to explicit on an example again. So you start with the permutation, say this one, and you draw the permutation table of the permutation in a weird convention for some reasons. So the first entry is a 5, so you put a dot at coordinates 5, 1. The second entry is a 2, so you put a dot at coordinates 2, 2. Third entry is a 6, so you put a dot at coordinates 6, 3, and so on. Now that you got this, you need to highlight the descents of the permutations. As you go up in this permutation table, whenever you go left, you want to highlight this with a red segment. And now here's the magical trick. You got to flatten the picture. So you take a picture, you press on it vertically. Okay. Yeah, flatten too hard. Okay. So you flatten it as hard as you can, and I can't do that anymore. No, it's not an issue. Okay. So you flatten the picture. You press it vertically in this way, allowing the segments to bend, but not to pass a vertex. So that's the way it goes. And well, theorem is that's a bijection, which is pretty nice. It's a bijection with this object that we call non-crossing arc diagram. Each of these 3 wiggling lines is an arc. So you have 3 arcs here, not 2. And well, I have to be precise about what is my arriving set. This is, so what I mean by arcs do not cross. So the first one is a crossing. Of course, the second and third one are degenerate cases of crossings. And the fourth one is not a crossing. That's not a crossing. Oh, great. Thank you. Thank you. So the fourth one is not a crossing. The others are. Now, I said this bijection is nice. Okay, it's nice looking, but why is it nice? It is nice because it completely trivializes the idea of canonical joint representations in the right weak order. I explain. So if you replace all permutation in your lattice by these non-crossing arc diagrams, then the canonical joint representation of this diagram is just going to be the set of 1 arc diagrams for each arc of this diagram. So you just have to separate this arc from one another. You get a bunch of arcs. Each of these is a non-crossing arc diagram. And each of these corresponds to a permutation. And these permutations are the canonical joint representation of this permutation. So that's why it's nice. And in particular, the joint irreducible permutations will be in correspondence through this bijection with the single arcs diagrams. So really, these arcs encode the joint irreducible and canonical joint representations in the right weak order. Everything clear? Yes. Why is this one going this way? Well, an arc. So the question was, why is this arc going this way? Maybe I can just go back to the bijection. You start. This is this descent, this segment. Yeah, I have a pointer. This descent, as you press it down, it cannot pass a vertex, and so this vertex is below this segment. So it's gonna. The segment has to bend upward, but this one is above. So as you flatten it, this part has to bend downward. And so as you press it, it has to look that way. More formally, an arc is just two endpoints, and for each point in between, you choose whether you go above or below. Okay. Okay. So what this means in terms of simplicial complexes is that we have a nice combinatorial model for the canonical joint complex of the right-weak order. We call it the non-crossing complex. Well, we call it, reading calls it the non-crossing complex, and it's just put a vertex for each arc and put an edge in between two arcs whenever they do not cross in the way we've seen before. So that's nice depiction. One other powerful combinatorics underlying between arcs is resides in the forcing order of the right-weak order. Remember, is this order on the join irreducible elements, and in this case, it just corresponds to the extensions of arcs. All right. Now, I just want to save some time and say in one slide just as much as I've said so far, by saying that everything is still true if I replace join by meets and flip some things everywhere. So everything has a counterpart. So we have canonical meet representations where we have the meet of nothing on top and the meet of many people on bottom. And we have the canonical meet complex associated to it, which looks oddly familiar. In fact, they're in bijection. And of course, we have another bijection between permutations and non-crossing arc diagrams, where instead of highlighting descents, we highlight the ascents. And in the same way, we just press it down. So we have one bijection that trivializes canonical join representations, and the other one trivializing canonical meet representations. All right. So now I can introduce what we've been working on. Namely, we tried to introduce something about, well, we introduced something about the canonical representations of intervals rather than elements. And it goes that way. Just the canonical representation of an interval is just the canonical join representation of the bottom element alongside the canonical meet representation of the top element. So when you have this interval, you just look at the bottom element from below and at the top element from above. And somehow this yields some nice results. So it's quite natural, after what we've seen, to introduce a simplicial complex that encodes these representations, whose vertices is going to be just the disjoint union of join and meet irreducible elements, and whose faces are going to be disjoint union of bunches of irreducible elements, such that the first one is a canonical join representation, second one is a canonical meet representation, and we want the element that is described to be one on top of the other one, or otherwise it's not an interval. And now what we can say is, well, first, it is indeed a simplicial complex. Second, it is flagged as well, just as before. And third, it behaves just as well with taking quotient as the structure we've seen before. So it's a nice extension of everything we've done so far. Okay, again, our example. Now I have two copies of my lattice because I want one to be labeled with the canonical join representation of elements, and the other one with canonical meet representations of my elements. And now I want to build intervals in this. And one way to do this is, okay, I can take top intervals. I want the top element to be this one, the meet of nothing. And the bottom element can be pretty much anything. So I get naturally a copy of the canonical join complex in the canonical complex. In the same way, well, if I can build an interval that is a bottom interval, whose bottom element is going to be this one, and whose top element can be anyone. So I get a copy of my canonical meet complex. And now I have to add things because there's more interesting intervals. And since I said that it is flag, I can just look, I can just build edges and everything would follow. So what I'm interested in is I take a join irreducible, say A, I look at everything that is above, and I just look at the meet irreducible above him because the other one would just follow. So I have G, H, F, and D. So I had these four edges between A, F, G, B, H. Now, in the same way, B is below only those four, yeah, I think so, meet reducible elements. So I get these four edges and I go on and go on. And this is the canonical complex of our toy example lattice. Now, I said it behaves just as well with taking quotients, so I'm going to take quotients. Here we already seen what taking quotient means. It means I just build my classes. I take the same the same ideal of the forcing order, and so I have the same congruence. I take the minimal of the classes and look at the induced posets. On the right hand side is slightly different because, well, everything is reversed because it's meat, so I have to take the top elements, but well, basically the same. So on the left-hand side, I contracted A and D, and on the right-hand side, I had to contract something a little different. I had to contract E and F because I have this bijection between join and meet reducibles. And what happens in the canonical complex is just, okay, I have to remove A, I have to remove D, and I have also to remove E and F, which are conveniently opposite side from A and D in my drawing. So I didn't do things just randomly. And we get this smaller simplicial complex on 6 elements that is the canonical complex of the quotient lattice. Okay. Now, about the weak order, because, well, it's the title of the talk, so I got to talk about it. Say I take an interval of permutations of size 6. So this one is smaller than this one in the right weak order. And what we're going to do is just naturally we need to look at the join representation of the bottom element and the meet representation of the top element. So we're going to take the join diagram of the bottom element and the meet diagram of the top element and just superimpose them. Okay, that's mapped. It's going to be bijective if everything works well. It's quite obvious that this is going to be injective because, well, this map is injective and this one as well. So, okay, it's injective and it's bijective on its arriving sets, but I have to say what this arriving set is in terms of combinatorics. So these are what we call the semi-crossing arc bidiagrams. So what are the constraints on this? We've seen that we can have crossings, so things can happen. So of course, I want the wet one to be a non-crossing arc diagram. So same rules as before. I want the blue one to be a non-crossing arc diagram. So same rules as before, but in blue. And I need some sort of compatibility relation between those arcs. Namely, they can have crossings provided these are good crossings. And this one here is a good crossing, and this one is a bad crossing. These two are degenerate cases of crossings, and same as before, this is not a crossing at all. So these are the constraints on my 2 non-crossing arc diagrams so that together they form a semi-crossing arc bidiagram. Between, it's the one that's going up and the one that's going down is not the same. So here, this is the blue going up. Well, it's going more up than the red one, and the red one is going down. So this is allowed. But if you flip all colors here, you will get something that is not a semi-crossing arc bidiagram. It won't be allowed. Okay. Okay. Now, just as before, this gives a nice combinatorial interpretation of the simplicial complex, the underlying simplicial complex. So the canonical complex of the weak order is in bijection with what we call the semi-crossing complex, which is basically you put a copy of each arc in one in blue and one in red. And you put an arc in between 2 arcs, if and only if then do not semi-cross. So on the top, you have the non-crossing complex in blue. On the bottom, you have the non-crossing complex in red. And in between, you have all these arcs that do not semi-cross. Now, what this allowed us to do, this structure, is to compute generalization of the Kreyvaer's complement. So the problem is the following. You pick a congruence, lattice congruence of the weak order, and you look at one of the classes. It is an interval. And I give you the canonical meet representation of the top element. How does it behave on top? And this completely determines my class, my interval, because I know what the congruence is. And the question is, how can you give me the canonical join representation of the bottom element? So we managed to compute this with an algorithm that I would not detail here. I just point out what's the connection with the Cravath complement, because it's not obvious. So you just have to pick the right congruence. The right congruence you have to pick is the one that contracts all arcs, but those shaped like this. It is the Sylvester congruence. The associated quotient lattice is the Tamari lattice. And in this case, this problem amounts to the is solved by the classical Cravath complement on non-crossing partitions. So just very briefly, this is what the classical Cravath complement looks like. You have a non-crossing partition, you intertwine dots in between, red dots in between the blue dots, then you link together anyone that's in the same connected component of the half plane, and you forget about the blue ones, and you get this. And maybe you can see that if you don't intertwine them here, but just put them on the same vertices, you're going to have these things that are, in fact, non-crossing. They're crossing in the right way. Well, that's all I wanted to talk to you about. I just want to conclude with a nice picture of the semi-crossing complex for n equal to 4. And thank you for your attention.
Questions?
Lovely talk. So does this give you a nice way to characterize all of the possible interval types in the weak order, like of some rank?
Intervals types?
Yes. What kind of posets could appear as an interval in the weak order of a given rank? So maybe up rank 7.
Okay, we haven't thought of this. One easy thing is, okay, you have this bijection between intervals and semi-crossing arc-by diagrams. And one easy thing is directly encoded how many cover relations has the top and bottom element. But everything that's in between, I don't know. We haven't thought of this. Not yet. So the type B non-crossing arc diagrams are, I think, currently being written down by Nathan Reading, Emily Barnard, and one of the student, I think, I don't recall the name, Tharp. So yeah, they're working on type B non-crossing arc diagrams. This has also been a little studied in from the geometrical point of view in the shard polytope article from something like last year. But in this case, no, I don't know how to look at intervals of the type B weak order.
Is the construction of this complex is universal? That means for every complex, do you have the reverse construction where you can?
Sorry, can you? I
so
can't
for
hear you
any
well.
complex, can you construct a poset for which you get this complex as a CJP?
I'm sorry, I have trouble.
So is this construction of complex is universal? So that means given a complex, can you construct a poset for which this
okay, is the question, can I go back from the complex to the can I wouldn't think so. I wouldn't think so, but I'm not sure.
That brings to the next question. Like, what are the restrictions on the complex that you get?
Oh, okay. So we don't know much about the complex. It is not pure. It is, well, it is flag. That's something, but that's really all we know.
The flag is universal. So every complex can be thought of as a flag of something up to homomorphism.
I don't know.